Welcome back, meine Damen und Herren. Yes, welcome, my ladies and gentlemen. We are now getting into our third unit, and this unit is about electromagnetic radiation, the quantum mechanical model of the atom, and quantum numbers. And then finally, we can put all that stuff together and get some electron configurations going. And this is really cool stuff. This quantum stuff is hard to understand, but it is really cool stuff. And the place we have to start to understand this whole idea of um, quantum mechanics is with electromagnetic radiation. So let us get started here with our discussion of electromagnetic radiation. Consider the form of electromagnetic radiation known as blue light. Oops, how about known as blue light? Yes, blue light. Does it consist of waves or particles? Egads, where do we start? Well, I kind of want to know what electromagnetic radiation is. So let us get into that. What is electromagnetic radiation? Wow, radiation. These polysyllabic words really challenge my spelling, don't they? Electromagnetic radiation. Well, to put it simply, electromagnetic radiation is a form of energy. That's all it is, really. Um, you know it. You know it in terms of it's stuff like light, X-rays, gamma rays, radio waves, microwaves. All of these are forms of electromagnetic radiation, which is really nothing but a form of energy. Good. Now, the question was what? Let's go back here. I think I'm forgetting already. Oh, look it. We want to know if this is a wave or a particle. Well, let's ask us this question, and we might want to leave a little space here. They have particles, particle props, we'll call them. Properties, and wave properties. Properties. There we go. Probably should have spread these out a little more to give us some more space. Well, what are some properties of a particle? Think of a particle like a baseball, or hey, this is football season. The Bears are playing Green Bay tonight. So, what are some properties of a football? Well, it has a beginning, it has an ending, um, and it's not thrown out. When I throw a football, it's not like I throw to the football and it goes out and it oscillates continuously infinitely long, right? When I throw a football, I have a beginning of a football and an end to the football, and if I throw it halfway well, it spins real well, but there's a beginning and an end. You might say that there is a chunk of a football, right? And so it has a beginning and an end. And when I catch the football, I catch it as one football, not a string of infinite footballs, right? It's not like this is just one big football and it oscillates forever, and I catch it over here. Here's my football helmet, and here's my face. I look more like a ghost. And here I catch the football and I run for a touchdown. No, it's not that I get this whole infinite piece of football that is thrown from the quarterback and caught by the receiver. It's the quarterback throws it, there's a chunk, he leaves his hands, and then the receiver catches it and he runs for a touchdown, and then it's just one chunk. Okay? So that's kind of a major property of a particle. Now, what are properties of waves? Well, let's look at a wave. A wave looks something like this, right? Yeah, oh boy, I did that pretty well for a change. Good. Now, what are some properties of waves? Well, they have something that is called a wavelength. And be careful here because a lot of people get this definition wrong. What is a wavelength? Well, wavelength, and here's the sign for a wavelength, lambda. A wavelength is the distance between corresponding points on adjacent waves. Now, does this say here that it is the peak to peak distance? Does it say that it's the peak to peak distance? No. Does it say it's the trough to trough distance? No. Does it say it is any 2 points on a wave? No. What does it say? It says that it is the distance between corresponding points on adjacent waves. That is the right definition. So this distance right here is a wavelength, but just as well this distance from this down. Notice this is, we're kind of going on the down slope here, down slope. They're the same points. The distance from here to here is also a wavelength. So don't look at peak to peak or trough to trough as the only definition of a wavelength. So that's my wavelength. Now, what else? What other characteristics do wavelengths have? And I better draw another wave because I'm going to need to draw another picture here. Waves also have something called frequency. They have a frequency. And that is, the frequency is the number of waves which pass a given point per time. And usually this is per second or per minute. Usually it's per minute or per second. So 20 waves per second, 20 waves per minute. And what do we mean by that? Okay, let's assume that I'm laying down right here. Here's my head. That's nice. And here's my chin and my mouth, and I have a nose, and then I have an eyeball. There's my eyeball, right? And I've got a little bit of hair, and there we go. And what is my eye doing? My eye is watching this area right here, and this wave is going in this direction. And so I'm just watching this point right here, and I'm counting. I have my little stopwatch here, yoink, and there's 12. And there's 6. I have my stopwatch here. I press the stopwatch, and I start counting the waves which pass by my eye in a given time. Well, that's what frequency is, and the symbol for frequency looks like that, mu. So that's frequency, and that's wavelength. Now, we can also have on a wave what? Amplitude. How high is my wave? But we don't talk a whole bunch about amplitude. We focus on wavelength and frequency as the big properties that we're looking at. Okay, good. So, can we answer our question yet? Which of these is electromagnetic radiation? Is it a wave or is it a particle? And the answer to this question is it is neither. Yoink. What is electromagnetic radiation? Electromagnetic radiation is not a wave, and it is not a particle. It is what? Let's go down. Oops. What is electromagnetic radiation? It is a wave particle duality. Duality. What does that mean? Well, a wave particle duality means what? That electromagnetic radiation has characteristics of both waves and particles. It's not a wave, it's not a particle, it's light. It's electromagnetic radiation, and it has characteristics of both. And specifically, what characteristics does it have? Well, it interacts with matter like a particle. That means it is emitted and absorbed in chunks that we call, which you'll learn more about soon, chunks called quanta. And what we like to say is, hey, electromagnetic radiation is emitted as a photon. And what is a photon? I hate this definition, but it's really about the only one I have to work with. And a photon is, we call it a particle of electromagnetic radiation. But here we go. We're going to make this contradictory. That has no mass. You say, wait a minute, how can a particle not have mass? Well, for a photon, we're saying it's a particle that has no mass and carries a chunk of energy, a packet of energy called a quantum. Okay, so that is the property of electromagnetic radiation that is particular in nature, right? It interacts with matter like a particle. That means it is emitted and absorbed in chunks called quanta. It is emitted as a stream of photons. Good. Now, what aspects does it have that are wave-like? Well, it is wave-like in that it travels through space like a wave. And that means what specifically? It has a wavelength and it has a frequency. Okay? So it has a wavelength and it has a frequency. Great. And so those are the aspects that make us think that, remind us that it has wave properties. Okay, so we answered our question. Does it consist of waves or particles? The answer is neither or both, right? It consists of waves. No, it's neither. It's not both. It is, what is it? It consists of itself. It is what it is. Electromagnetic radiation, which has characteristics of both. Characteristics of both. And that's why we call it a wave-particle duality. Next, consider blue light and X-rays. Which has the largest wavelength? Boy, I wish that we had I wish we had something like like a chart that would order wavelength for us. Hey, look at this. This is called the, let me get rid of that. Let's try that again. Let's try to get rid of those. I hate that. Okay, we'll leave it. I think. Look what we have here. We have the electromagnetic spectrum. And what is that? Well, if you look here, this is all kinds of electromagnetic radiation. And it's in order. And it's ordered how? It's ordered by wavelength. So what is my electromagnetic spectrum? Electromag radiation ordered by wavelength. Okay, that's my electromagnetic radiation. And you're going to see something very interesting here. Okay, so here's wavelength. And also, this is wavelength in meters. Here's wavelength in nanometers when we come to the visible light spectrum. Notice how little of what we see is included in the electromagnetic spectrum. We can't see gamma rays, we can't see radio waves, we can't see infrared or X-rays or ultraviolet, but we can see Roy G. Biv here, right? This is Roy G. Biv, or in reverse, Roy G. Biv. Roy G. Biv, right? And what is that? Red, orange, yellow, green, blue, indigo, and violet. So that's the way to remember the visible spectrum in order. Roy G. Biv, starting at high wavelength, that's 750 if you can't see it now. From high wavelength to low wavelength, Roy G. Biv. Good. All right, so here is our tool, and the question was blue light and X-rays, which has the largest wavelength? Okay, largest wavelength. We have blue light, which is blue light looks like it's right around here, and we have X-rays, which are here. Here's my X-rays. Be careful here. This is okay. So I have 500 nanometers here. This is about 500 right here. 500 nanometers here. Here is my X-ray. Which one is smaller? Smaller is this way. This is smaller when it comes to wavelength. And so my X-rays have a smaller wavelength. Good. So X-rays are smaller than blue light. Okay, which has the highest frequency? Can we get any information here out of frequency? Okay, I think we can. Here, folks, let me clean this up. Just like magic. Don't you love that? Good. Frequency. Here is frequency. Now, what do you notice about frequency? Frequency is increasing going in this direction. Wavelength was increasing going in this direction. And we have a relationship that's important between wavelength and frequency, and that is C is equal to lambda nu, meaning the speed of light is equal to the wavelength times my frequency. And what's cool about this is the speed of light is essentially constant. And it's constant at 3.00 times 10 to the 8th meters per second. Okay, now if that's constant, what does that really mean? That means that my wavelength is inversely proportional to frequency. And you guys all know what inversely means, right? When my wavelength goes up, what happens to my frequency? My frequency goes down. Good. So if I have big wavelength, that means I have low frequency. Good? Outstanding. So let's go back to our question here. Which has the highest frequency? Well, remember we said they were inverse. Here's increasing frequency. Blue light is somewhere in here. X-rays are here. Increasing frequency, that means X-rays have higher frequency. So my blue light is less than my X-ray. Which has the most energy? Aha, boy. Do you think there's a relationship somehow between energy and frequency? And there is indeed. Energy is equal to h nu, and h is Planck's constant. Planck's constant. We'll learn more about Planck soon enough. Constant, and that is a number you really don't have to know, but we can say it. It's 6.626 times 10 to the minus, it's a very small number, 34 joule seconds. Now, do you need to know that? No, you don't need to know that. Energy, energy, and let's say energy of a photon, okay? The energy of a photon is equal to Planck's constant times frequency, okay? So let me rewrite that so it's nice and pretty. Energy of a photon is equal to h nu, right? That's one important thing. So as frequency goes up, what happens to energy? Energy goes up. Now, we also know what? We know that if we look up here, C is equal to lambda nu, so nu is equal to C over lambda, right? So that's another way to think of that. And then we can also then substitute that down here. And what do we get? If I substitute, then I get E of a photon is equal to H. What was that? C over lambda. HC over lambda. So these are two ways to figure out energy. When my wavelength goes up, what happens to my energy? Well, wavelength is in the denominator, so that when it goes up, that means my energy is going to go down. When nu goes up, what happens to my energy? My energy goes up. So I think we can answer our question here. Which has the most energy? Well, X-rays have the highest frequency, so that means X-rays have the highest energy. And finally, which travels the fastest? Well, we talked a little bit about the speed of light. And what did we say about the speed of light? The speed of light is constant for all forms. What does that mean? That means all electromagnetic radiation travels at the same speed. So, hey, all travels at same speed. And what is that speed? That speed would be what? 3.00 times 10 to the 8th meters per second. Remember, units are important. All right, good. Here we go. I'm going to let you do this one, and then we'll call it quits for this lesson. Green light, yellow light, and gamma rays. Arrange them in order of increasing wavelength, increasing frequency, increasing energy, increasing speed. Okay, I'll give you a few minutes for this. Put me on pause and thaw me when you're ready for the answer. Okay, so let's look at our electromagnetic spectrum. And we want to, let me clean this up again a little bit. We want to look at what? Yellow light. Okay, so here's yellow. And we wanted to look at green. Here's green. And remember, both of these guys are really right in this area called visible spectrum. And we wanted to look at what? Yellow, green, and gamma. And where's gamma? Gamma, 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 gamma. Oh, here's gamma. Wow, it's way over here. And what is this? This is what? Low wavelength. Oh, here's high wavelength. This is frequency, low frequency. This would be high frequency. And if we put energy on here, let's put energy right here. What do we know? Energy is what? Energy is inversely proportional to wavelength and directly proportional to frequency. So when I have high frequency, I have high energy. So here I have high frequency. That means I have high energy. That means I must have low energy of photons on this side, right? So that's low energy. So that means it's increasing going in this direction. Okay, so let's get our answer. Increasing wavelength. Well, it's going to start off with gamma has the lowest wavelength, and then green is higher, and yellow is the highest of these three. Frequency, hey, it's just the opposite. Yellow is the lowest, green is next, and gamma is next. Increasing energy, hey, increasing energy is just like increasing frequency, right? Because energy is equal to H nu. It's a nice nu there. Sorry about that. So as my frequency increases, my energy increases. Good. So that would mean I have yellow going to green, which is more energetic than yellow, and then gamma, which is very energetic. And then increasing speed. Well, what do we know about the speed of light? C is constant for our purposes, right? And that means what? All of these are the same. Yellow travels equally as fast as green, which travels equally as fast as gamma, which travels about 3.00 times 10 to the 8th meters per second. Cool. All right, let's call it quits right now. I'll see you next time. Enjoy. Auf Wiedersehen.